All right, there we go. So before we kind of get into the unit circle, I have a question for you guys, and I'm going to put in the poll section here. Did your advanced algebra trig class make it through the unit circle last year? So we've got three options there. Yes, I've got fond memories of the unit circle, or I think we might have, but I don't remember it all that well, or I have no idea what you're talking about. How are we feeling about the unit circle? Okay, right at the end of the year. Yeah, so it's still kind of during that COVID season. Guess we're still in the COVID season, but not quite as much. Or with school not being quite as ambiguous as it was then. Okay, you remember it a bit from geometry? All right, closing the poll in 10 seconds. So if you have not voted, feel free to vote. Okay. So it looks like we are fairly evenly split, with the majority feeling like they remembered a little bit, but not amazingly. So that's all right. We are going to go through the unit circle, kind of what it is, how it's helpful, stuff like that. So go ahead and grab your notes and let's get going. So 4.3, the unit circle. All right. So the first thing that we want to do for the unit circle is draw it. So I'm going to make a nice big coordinate thing here. And then I'm going to do my very best to draw a circle. We'll see how this goes. Hey, not bad for a freehand circle. All right. So the first thing we want is a unit circle. And it's called the unit circle because the radius is 1 unit. So this would be the coordinate 1, 0. This would be the coordinate 0, 1, negative 1, 0, 0, negative 1. Okay. And so anytime I draw a radius out from this circle, we know the length of that radius is 1. And so this helps us, it's going to help us to find sine, cosine, and tangent. And then also, along with that, secant, cosecant, and cotangent for a lot of common angles. So we're going to talk about those common angles in degrees and in radians. And so then we'll be able to find sine, cosine, and tangent for a lot of these common angles. And it's also, these angles are based off of special right triangles. So if you remember special right triangles from way back in geometry, then these should be fairly easy to remember. If you don't, that's okay. We're going to kind of bring it back to that. So first thing we're going to do is we're going to draw some lines out from the center here. There's going to be 3 in each quadrant. And if you can, try to make this gap as big as this gap, and these gaps be about half the size of this one, because what we're going to do here is we're going to have coordinates and angles and all kinds of stuff going along here. What we're talking is these angles here. So this is going to be a 30-degree angle for this line. This one's going to be a 45-degree angle. And this one's going to be a 60-degree angle, going back to the positive x-axis. And then this one is 0 degrees. So we'll go through it in degrees first, and then we'll go through it talking radians. So the bigger gaps are going to be 30-degree gaps, and the smaller gaps are going to be 15-degree gaps. So then this one is 90, because 60 and 30 is 90. And then we're going to make those 3 in the next couple of quadrants as well. And again, we're just doing our best to make these lines. So this one would be 120 degrees, 135, 150, 180. And then we're going to draw some more. 210, 225, 240, 270. And then our last quadrant, $300, $315, $330, $360. So 0 and $360 kind of reside in the same location here. Okay. So now we've got the degrees on our unit circle. Now we want to go through and put the radians down as well. So there's different ways to kind of think about how we want to put the radians down on the unit circle. There's easier ways to remember and kind of harder ways to remember if you were going to kind of reconstruct this whole thing. So one way that you can think of it is in the same way that these gaps were 30 degrees. The larger gaps are pi over 6 degrees or pi over 6 radians because pi over 6 is equal to 30 degrees. And then the smaller gaps are pi over 12 because pi over 12 is equal to 15 degrees. But then that involves a lot of adding fractions and whatnot. So another way that you can think of it is that the larger gaps are 2 pi over 12, the smaller gaps are pi over 12, and then we'll go back and reduce all of the fractions. So that's another way that we can kind of think of this. So that's how I'm going to start with it. If I was going to just kind of construct the unit circle here, this first one would be 2 pi over 12, which is really pi over 6 when you reduce it. Then this would be 3 pi over 12, which is really pi over 4 when you reduce it. This one would be 4 pi over 12, which is really pi over 3 when you reduce it. Then, since this gap is a bigger gap, it would be 6 pi over 12. Because we'd add 2 to the previous, which if I reduce this fraction is just pi over 2. So we can go about it this way, or you can take each of these degrees and then convert them into radians. Whichever way you want to do it is fine. But continuing in this fashion, 6 pi over 12 plus 2 would be 8 pi over 12. Reducing that fraction, we would get 2 pi over 3. Then we'd have 9 pi over 12 and 10 pi over 12. Reducing these fractions, we would get 3 pi over 4 and 5 pi over 6. And then adding 2 pi to that, we get 12 pi over 12, which is just pi. And we should, that's kind of another spot that we can check ourselves because we do know that 180 degrees and pi are equal. So if we get to this point where we're at, okay, that would be 12 pi over 12, that's pi. That's kind of a good indicator that we started off correctly. Okay, so then continuing on in that same fashion, 14 pi over 12 for the big gap, which is then reducing to 7 pi over 6. 15 pi over 12, which reduces to 5 pi over 4. 16 pi over 12, which reduces to 4 pi over 3. And then 18 pi over 12, which reduces to 3 pi over 2. Okay. And then 20 pi over 12, which reduces to 5 pi over 3. And then 21 pi over 12, which reduces to 7 pi over 4. 22 pi over 12, which reduces to 11 pi over 6. And then we're back to the beginning again where we have 0 pi and 2 pi. Because 2 pi is all the way around the circle. Okay. So now we have degrees and we have radians. Now here's the fun part. The part where we actually get to think about things like special right triangles and x and y coordinates and sine, cosine, and tangent and all that good stuff. So first thing I want to do is kind of pull off to the side this triangle right here. If I were to like drop a line down and make a right triangle here where this angle theta is 30 degrees. So I'm going to pull that over. So if I know that's a 30-degree angle, and I know that that side is 1 because this is my radius here of my unit circle, which is 1. And I know then this is a 60-degree angle. Well then, using our special right triangles, I know that the short side of a 30, 60, 90 is half the hypotenuse. So half of 1 is 1/2. And then I also know that the long leg on a 30, 60, 90 is root 3 times the short leg. So root 3 times 1/2 is root 3 over 2. Well, this horizontal distance here is my x coordinate for this point. And then my y coordinate for this point is this vertical distance here, that 1/2. So we have root 3 over 2 and 1/2. So that's a 30, 60, 90. And it just so happens that if I were to do it for this triangle over here as well, we'd also end up with a 30, 60, 90. It's just with the coordinates swapped, because this horizontal distance would be the shorter leg and the vertical distance would be the longer leg. So we would end up for this coordinate being at 1/2 root 3 over 2. So we kind of have both of our 30, 60, 90s figured out. Then the 45, 45, 90 here. So this one, if I were to drop something, drop a vertical down and make a right triangle, we'd end up with 45, 45, 90. So we're going to take a look at that next. Okay. So for a 45, 45, 90, we end up with root 2 over 2 for both of the legs, because both of those will be the same. And that actually comes from the Pythagorean theorem. So then both my x and my y coordinates are root 2 over 2. Because really it's the hypotenuse divided by root 2, but we don't want to write it with a root 2 in the denominator. So then we rationalize the denominator and we get root 2 over 2. Okay, so all the rest of the quadrants come from these three, come from the first quadrant. It's just varying positives and negatives for each of them. So we know that in the first quadrant, everything's positive. Both coordinates are positive. In the second quadrant, though, the x's are negative and the y's are positive. And then in the third quadrant, everything's negative. And in the fourth quadrant, we have positive x's and negative y's. So pretty much everything from here, I'm just transferring over to each of these. So for example, with this one, this is my 30, 60, 90 here. So we'd end up with negative root 3 over 2, 1/2. Here's my 45, 45, 90. We'd end up with negative root 2 over 2, positive root 2 over 2. And then here's my other 30, 60, 90, this version of it. We'd end up with negative 1/2 root 3 over 2. So we can do the same thing, just copying this all the way around. So let's do that. We end up with both of them negative in this quadrant. So we get, this is our little 30, 60, 90, or like the shorter y value. So we get negative root 3 over 2, negative 1/2. Here we get our 45, 45, 90, negative root 2 over 2, negative root 2 over 2. Here we get our other 30, 60, 90, but with the larger y value. So we end up with negative 1/2, negative root 3 over 2. And then over here, the y's are negative this time, and this is our 30, 60, 90 with the larger y value. So it's the 1/2 negative root 3 over 2. Here's our 45, 45, 90 with root 2 over 2, negative root 2 over 2. And then our other 30, 60, 90 with root 3 over 2, negative 1/2. All right, so that is the whole filled in unit circle. And we might go, well, that's really nice. Now we know all of these coordinates and stuff like that, but what does this actually do for me? So what this actually does for us is it helps us with sine, cosine, and tangent for these common angles. Because I'm going to tell you this identity and then we'll kind of see where it comes from. So let's put it up here. Cosine is x, sine is y. Because if we look at this 30, 60, 90 that we pulled from right over here, sine is opposite over hypotenuse, which in this case is 1/2 over 1, which is just 1/2, which is the y value. So this is how we know the sine of 30 degrees is 1/2. Then cosine is adjacent over hypotenuse, which is the x value over the hypotenuse of 1. So it would just be root 3 over 2 for cosine, which also corresponds with our x value. So if I ask you for cosine of 30 degrees, you look at your unit circle and you get root 3 over 2 because that's the y value on the 30 degrees. If I ask what's the sine of 7 pi over 4, we find 7 pi over 4 down here, and we know that sine is y, so that would be negative root 2 over 2. So this is how we find common sine and cosine values. We can also find tangent from this, because tangent is opposite over adjacent, right? So tangent being opposite over adjacent here, 1/2 over root 3 over 2, that's just the y value divided by the x value. So cosine is x, sine is y, tangent is y over x. So then from there, you can also get secant, cosecant, and cotangent. Because, and let's kind of maybe organize this a little better down here. Cosine is x, Sine is y. Tangent is y over x, because then we can see that then secant is going to be its cosine flipped, right? So that would be like 1 over x. Cosecant, 1 over y. Cotangent, x over y, because you just flip them. So flip cosine, flip sine, flip tangent to get secant, cosecant, and cotangent. Okay, so we're going to get a little bit of practice here with finding things on the unit circle, figuring out what sine, cosine, and tangent are for some common angles. So let's find, we'll start with sine of 120 degrees. Then we'll do cosine of 4 pi over 3. We'll do tangent of 225 degrees. And we'll go from there. Okay. So looking at our unit circle, sine of 120 degrees. Well, we know that sine is y. So I go over to 120 degrees. And we notice our y value, which is root 3 over 2. So that would be the sine of 120 degrees, root 3 over 2. And what's nice is it gives it to us in exact form, because if you type this into your TI-84, it's going to give you a decimal. And a lot of times you'll be asked for it in exact form if it's an angle like these, one of these special right triangle type of angles. All right, so then cosine of 4 pi over 3. Anyone think they know cosine of 4 pi over 3? Feel free to find this one and then put it in the chat. All right, 4 pi over 3 is over here. Cosine goes with x. So what's our cosine of 4 pi over 3? That would just be the negative 1/2, right? Yeah, exactly. So we find 4 pi over 3 in our unit circle. We find the x value, negative 1/2. All right, tangent tends to be the one that's a little bit more difficult just because usually it involves canceling things or flipping and multiplying because we're dividing with fractions and stuff like that. So if we go to find tangent of 225, first we have to find 225 on our unit circle. It's right over here. And we notice that the x and the y value are both negative root 2 over 2. So tangent is y over x. So y over x would be negative root 2 over 2 over negative root 2 over 2. And in this case, they cancel each other out completely. But if we weren't sure about that, we could always flip and multiply. So that would be negative root 2 over 2 times, flip this, so it would be 2 over negative root 2. And then we'd cross cancel stuff. Those would cancel with each other, those would cancel with each other, and we'd get 1. So the tangent of 225 degrees is 1. And you can always type these into your calculator and double check to make sure that it matches up with the decimal that you got. If you got a decimal, like in this case. But yeah, anyway. So there's a couple of them. Let's do a few more. Let's do some with secant and cosecant and cotangent. Let's find the secant of 11 pi over 6. And then we'll find the cosecant of 90 degrees. And then the cotangent of 150 degrees. Okay, so secant of 11 pi over 6. So secant means we flip cosine, and we know cosine is x. So if cosine is x and we are looking for 11 pi over 6, that would be right over here, 11 pi over 6. The cosine value is root 3 over 2. So it'd be 1 over root 3 over 2, which means we just have to flip that fraction of root 3 over 2. So it'd be 2 over root 3. And technically, we don't want to leave it like that because we've got a root 3 in the denominator. So instead, we would multiply by root 3 over root 3 to get rid of the root 3 here. Because root 3 times root 3 is 3. And then we can just have 2 root 3 on the top. So this is the most widely accepted form of the answer. This is technically correct, but it's not in the proper form. So we want to make sure that we make it into the proper format without a radical in the denominator. Okay, so that's secant. You just take the cosine and you flip it. Cosecant of 90. So that's where we take that's where we flip sine, so it's 1 over the y value. So in this case, we look at 90 and go, okay, 90 is 0, 1. So 1 is my y value, which is my sine. And 1 over 1 is just 1. So cosecant of 90 is 1. If you get a 1 over 0 situation, it's just undefined. All right, and then cotangent of 150. So cotangent, you can either think of it as flipping tangent, or you can think of it as x over y instead of y over x. So that's kind of the way I prefer to think of it, as x over y instead. So we're going to find 150 degrees right here, and we're going to go x over y. So root 3 or negative root 3 over 2 over 1/2. And then we have to flip and multiply. And we can cross cancel the 2's. So we just get negative root 3 over 1, which is negative root 3. Okay. So that is one kind of problem you're going to be asked. What is sine, cosine, tangent, secant, cosecant, cotangent of these common angles that we're going to become more and more familiar with? The other kind of problem that you're going to see with this is actually considerably simpler. It goes off of this, but they usually end up working out really nicely. So we're going to go over the second type of problem as well, and then we'll be done. But before we do, are there any numbers we're not sure where they came from? Anything that we want to go back to at this point? Any of these 6 in particular, too, that we're not sure how we got the answer, because that's going to be important. Okay. So the second kind of question that we're going to be asked today and tomorrow and throughout the week is this kind. But before we get to that kind, I'm going to rewrite at the top. Cosine is x, sine is y, tangent is y over x, or rise over run. You can kind of think of it because tangent also is kind of, it's the slope. And then we have secant, cosecant, cotangent. Okay. So keeping that kind of in the back of our mind here as we go, here's the other kind of question that we're going to be confronted with. It's going to say a line intersects the unit circle at the coordinate let me grab one that's an actual one of our problems real quick. We'll say it intersects at 72/97, 65/97. And we want to know what is sine theta. And from this, we're going to go and find the rest of the trig functions as well, because then we don't have to keep rewriting the problem to do the same thing. Okay. So when you see problems like this, it's saying it intersects the unit circle at these coordinates. What is cosine of theta? The nice thing is, since it tells you that it intersects the unit circle, all you really have to do is cosine corresponds with x, so we choose the x value for our answer. That's it, 72/97. Well then, how about sine theta? What do we think sine's going to be? Sine goes with y, right? Yeah, 65/97. Or tangent of theta. Well, that would just be y over x, right? So doing a little bit of work here, but 65/97 over 72/97. If you have the same denominator, they just cancel. So you can flip and multiply if you want to make sure, but really you just get 65/72. And then if you have sine, cosine, and tangent, especially in this fraction format, it makes it really nice and easy to find secant, cosecant, and cotangent, because then I can just go, all right, well, what if I wanted to know secant of theta? Well, that's 1 over x, or flip cosine. So then I just flip cosine and get 97/72 for secant of theta. Well, and what about cosecant? Cosecant, you just flip sine, right? So 97/65. Or cotangent. Well, then we just flip tangent, so 72/65. So just given this coordinate and the fact that it intersects the unit circle, we can just use that to find all 6 trig functions. And the nice thing is, on your IXL section, you're only going to be asked to find 1 per triangle. Okay. So that's the other main kind of question that you're going to be asked today, and it's kind of an offshoot of the first type. Any questions as to how we got any of these numbers? Okay. Then let's go ahead and take a look at the kind of questions we're going to be asked on our homework. It's going to be pretty much exactly like the examples that we've just done. You're going to want to have your unit circle that you hopefully drew in your notes in front of you while you do your homework today. As we get more and more familiar with the unit circle itself. I'll also provide a filled in copy in case you didn't get all of it in your notes. But let's go ahead and take a look at the work for today. Okay, so we have two IXLs, M6 and M7 to a smart score of 80. M6 is the kind of question that we just did. Okay, the terminal side of an angle in standard position intersects the unit circle at 65, 97, 72, 97. So it's pretty much exactly the question that we just had, but with the coordinates switched around. What is cosine of theta? So we just grab the x value. Make a fraction. Make sure you hit the fraction button first, otherwise it doesn't seem to recognize it. 65, 97ths. Enter. All right, another one we're asking for cosine. So we've got 15/17 for our x value. So 15 on the top, 17 on the bottom. All right, let's find one where it's not cosine. Tangent. All right, we have 28/53 and 45/53. Remember, tangent is y over x. So y over x is going to end up being 45/53 over 28/53. Since it's the same denominator, we can just get rid of the 53 and get 45 on the top, 28 on the bottom. Okay. So that's one type of question that you're going to get. The other type of question you're going to get is trig ratios of special angles. This is where your unit circle is going to be the most helpful because we're going to be asked for things like sine of 30 and write your answer in simplified rationalized form. So that just means exact form. Sine, remember, goes with y. And so we look at our unit circle and go, okay, 30 degrees, the y value is 1/2. So 1 over 2. Tangent of 30. So y over x. So that's 1/2 over root 3 over 2. So that's where we have to rationalize a little bit. So kind of off to the side here. 1/2 was our y value. Root 3 over 2 was our x value. When we flip and multiply, we get 1 over root 3. So we have to rationalize that, multiply by root 3 over root 3 to get root 3 over 3. So we grab our fraction, root 3 on the top, 3 on the bottom. And then we get something like cosine of 60, where you just find the x value on 60, which was 1/2. So let's see if it has anything different for us. Sine of pi over 6. So sometimes it'll ask you for things in radians. Remember, pi over 6 is, yeah, we can do another tangent one. Remember, pi over 6 is the same as the 30-degree spot on your unit circle. And sine goes with y, so this would be another one where it's 1/2. See if I can find another tangent one. All right, well, one moment. Here we go, tangent of pi over 6. So this was actually the same one that we had been asked previously, tangent of 30. But when you do tangent of pi over 6, you remember that tangent is y over x. So you look at your unit circle, and the y value on pi over 6, or 30 degrees, is 1/2. The x value is √3 over 2. So you'd have 1/2 divided by √3 over 2. So 1/2 over √3 over 2. If you flip and multiply, you get rid of the 2's and you just end up with 1 over √3. But then, since you can't leave a √3 in the denominator, you rationalize by multiplying by √3 on the top and on the bottom, since that's like multiplying by 1. So 1 times √3 is √3. √3 times √3 is 3. So that's where we get √3 over 3. And if you want to, on your unit circle, if it helps later on, you can go through and write down what the tangents are going to be for each of them. So like we know, for example, that the tangent here is going to be √3 over 3 when you rationalize it. So if you want to write that off to the side, you can. Over here, the tangent's going to be 1. Stuff like that. This one, √3 over 2 over 1/2, would just be flip and multiply, you just get √3. So they're all going to be some variation of that. The tangents over here in the second and fourth quadrants will be negative, because tangent is also related to the slope of the line, and slope is negative in these two quadrants. And then they'll be positive in these two quadrants because slope is positive here. So that's another kind of a shortcut that you can take to get tangent. Or you can just do y over x each time. Does that kind of make sense? Cool. All right. So this is the part, and sorry, this class was a bit of a longer one than usual, but we had a lot of ground to cover, and tomorrow we're going to keep practicing this. This is the part where you guys get to go and work on the assignment, and if you have questions, feel free to stick around. If you decide later that you have questions, send me an email, come to office hours in the morning, make sure we get some help and are ready to go. So with that, go ahead and enjoy the rest of your day. I'll see you guys tomorrow. Feel free to stick around if you have questions.